Okay, the title of the talk is Dirac's large numbers in Einstein-Dicke cosmology. Please.
Hello, thanks for coming. Well, I'll talk about Dirac's large numbers in Einstein-Dicke cosmology. And I think this is an interesting attempt, and many people contributed to it. So it's kind of a long story, because the father of these ideas is somehow Ernst Mach, with his idea that gravity might be originated from the distribution of matter in the universe. And many people were fascinated about that, including Robert Dicke, the famous American astrophysicist. Einstein was very intrigued and said he incorporated Mach's principle in his theory, even if, as we shall see, that's not entirely true. Dennis Sciama was a cosmologist who made important contributions, and interestingly, Erwin Schrödinger had also thought about along this line. And I'm focusing today about Dirac's contribution, even if Dirac was the least aware of Mach's principles, so to speak. Okay, I mean, of course, this is something else than the standard cosmological model. If you're a believer of 70% dark energy and dark matter, it's of course something that would be to have reconsidered. Anyway, let's start here at general relativity and gravity. I mean, everybody knows of 1905, special relativity, general relativity 1915, but there are 10 years in between which are very, very interesting, almost unknown. And it turns out that the very first idea Einstein considered while developing general relativity was that simple optical analogy. From the just proved assertion that the speed of light in the gravity field is a function of position, it is easily deduced from Huygens principle that light rays propagating at right angles to the gravity field must experience curvature. So the very first thing Einstein assumed that there was a variable speed of light, that the mass is modified, that the speed of light was slower in the vicinity of masses, and everything worked like an optical lens. And indeed, that's today, as he said, one of the most common tests of general relativity, that we have a light deviation. However, there might be an alternative theoretical framework behind it. So, in the meantime, I mean, it has been developed by various authors that it's really equivalent. You can describe general relativity by a curved space with a constant speed of light, but alternatively also with a flat space and a variable speed of light. That's just two mathematical formalisms that apply to the same thing. And of course we have the speed of light by definition today, but if the speed of light is lowered in the vicinity of masses, if it changes, of course, the wavelength and the frequencies change accordingly, so you won't directly see a deviation from that value, that's clear, but of course you still have the evidence of light being deflected. So this is just a summary about this variable speed of light description of general relativity. You see that light is decreased in the vicinity, the frequencies, we have lower frequencies, we have accordingly longer time scales, we have length contracting and so on, and a couple of other physical quantities also show this same spatial dependency. And this is a very nice paper, one of these I mentioned, I like this particularly. And so we have, until here we have a one-to-one correspondence of general relativity in this variable speed of light model. And this is Einstein's original paper. And now look at this, we're talking about cosmology, and this is a very interesting formula for the dependency of the speed of light. We have here the gravitational potential, and it's just a tragedy that in 1911 there was no cosmology, you know? I mean, for Einstein, the universe was our galaxy. So he couldn't discover a certain structure that other people could discover, and one of the most yeah. Interesting developments here was a paper by Relativity in 1975. By the way, that's not Brown's ticket, that's a precursor of it. And Relativity says, okay, he also took the very same approach to Einstein. He corrected 1 factor 2, but it's basically the same approach that Einstein did in 1911. He said, look, the variation in the index of refraction about the sun is required is 1 plus something, okay? And here we have the gravitational potential of the sun, obviously. But what about the 1? Couldn't it be that it has to do with the universe? Does it have its origin in the remainder of matter of the universe? And this is a very interesting idea in the sense of Ernst Mach, because now you have the universe interfering with the gravitational interaction. And this leads to well, a quite simple dependency of the gravitational constants. The speed of light would be related to this sum, all the masses in the universe divided by the respective distances. And this is just a brief idea how in first approximation we would arrive at Newton's law. We have this dependency of the speed of light. You can rewrite this also in a more general sense. But anyway, we have local acceleration would be something like the gradient of the square of the speed of light, and by just differentiation and applying the chain rule, so this term in red would turn out to be the gravitational constant, which in fact, if you look at the orders of magnitude, is correct. Yeah, it's a very interesting coincidence as just for itself. So Robert Dicke also applied this to cosmology, and you might look at it. He said, let's take a minute, look at this. That matter is on the average fixed in position relative to the Newtonian coordinate frame. That means, and we soon come back to this, that means he challenges the usual interpretation of the cosmic redshift. Okay? And this again, of course, is related to Mach's principle. Don't forget that Mach was arguing very interestingly with this Newton's bucket argument, and he deduced that inertia, it might be very reasonable that inertia originates from all masses in the universe, and consequently, in a kind of equivalence principle or precursor of it, he said, well, therefore also gravity should originate from the universe. Okay, and that's where our hero enters, Dirac's large number hypothesis. Forget about this stuff I told you before, we're in a different mindset now. And Dirac wasn't thinking about the Mach's principles or gravity related to the universe. He was just thinking about numbers. He said, okay, we physicists, we should worry about numbers. These are measuring values. Theoretical physics also explain. Okay? Numbers, such as the fine structure concept. Yeah? There's an anecdote, young theoretical physicists coming to Dirac and explaining their theories, and he said, oh, just wait, can you explain the fine structure concept? No? So, come again when you have done it. Okay? And he spent years of his later life to worry about things like the mass ratio of proton and electron. And of course, he also wondered about this very strange very strange number, which occurs when you compare the electrical and the gravitational force in the hydrogen atom, nature's most simple structure in the universe, okay? And it's a huge number, 10 to the 39, almost 40 digits. It's an incredible number. Why is this relation so enormous? And Dirac was kind of desperate. There's no reasonable, no sensible mathematics I could imagine to arrive at that number. And then, eventually, the first measurements of Hubble in the 1930s came up, and he said, hey, look at that. If you take the radius of the universe and the radius of the proton, it's the very same number. Talking about orders of magnitude, okay? And this is a very intriguing idea, and in fact, many physicists to this day have investigated or inspired and still think it's very interesting. The problem is, and here you have to distinguish Dirac's first observation, which is already very interesting, from his second observation about the number of particles of the universe. There were estimates of the total number of the mass, and you divide by the hydrogen atom mass, and then you arrive at roughly 10 to the 78 particles in the universe. And that's the square of that first number. And Dirac said, okay, this is a very remarkable coincidence. It shows that there might be a deep relation between atomic physics and cosmology. Okay? The problem is here, the second hypothesis is in blatant contradiction to everything what we believe to have learned about cosmology. It seems just absurd. It just seems outlandish, because why a square? I mean, if you think about the cosmos and the universe, the number of particles, they should be related to the third power, because you get kind of a volume, don't you? And this is the reason, because people don't really distinguish between the first and second hypothesis. This is the reason why Dirac's ideas are dismissed to this day as numerology or fancy or whatever. Because the second hypothesis seems so, it contradicts not only the Big Bang, not only steady state, not every thinkable cosmology is just, well, you can't believe it, right? But there is a solution to this, based on ideas of Einstein-Dicke. I'll show you soon. Yeah, just as a sideline, I mean, even if Dirac didn't worry very much about Ernst Mach, Dirac's two hypotheses taken together, you can conclude then the Mach's principle, this coincidence, which is a very interesting one. But it's not the other way. You can't deduce Dirac's hypothesis from this interesting coincidence, what today we call that flatness. Okay, the gravitational constant is roughly related to the radius and the mass of the universe and the speed of light. Because this could be satisfied even if elementary particles would be, say, 1 million times heavier, and there would be 1 million times less in the universe. This would still hold. But Dirac's two observations, they go beyond. So, and, well, it's kind of a tragedy. Einstein and Dirac, they never talked about their best ideas. Definitely, I mean, Einstein wrote about in later years interesting things, but he definitely didn't know about Dirac, and so Dirac didn't know about Einstein either. And we have, this is, I think, the historical part of the talk. It's very, a tragedy of scientific communication that none of these people talked about their ideas, which are so closely related. Okay, the only almost everybody referred to was Ernst Mach. Dicke knew about Ernst Mach, Einstein, Sharma, and Schrödinger. Dirac didn't even know about Ernst Mach. And Dicke and Dirac, they had a very superficial conversation full of misunderstandings, but for the rest, nobody talked to each other. Think about that. So, however, Dirac was quite close to considering a variable speed of light. Unfortunately, unfortunately, he said, well, the speed of light is a constant. But it was kind of a contradiction to his own paper, because in his own paper he says, well, there might be evolution of the horizon, which, I'm sorry for that, this is 2/3 here. I have it in the other slide. So Dirac considered a model where the radius of the universe, the horizon, increased with absolute time to the power of 2/3. And then if he would add it, this very simple stuff, take the expansion rate of the universe just as the speed of light, just as the momentary speed of light, then from a very easy differential equation you get to this dependency deduced by Dirac later. The radius would expand as with the square root, and consequently the speed of light would decrease also with the square root of absolute time. Now, we have this cosmological evolution, and of course this has consequences. If the speed of light decreases with time, so the frequencies, so our clocks have to show a different behavior. Wavelength would have to decrease with time, and frequencies would have to decrease, and of course we have the time step itself, which would be longer. And so the behavior of atoms would change in time. Our best clocks are just atoms. So these atoms would send out smaller wavelength and would have a decreased frequency. However, so light that would be considered as fundamental measuring scales of light would decrease as long as atoms are regarded. However, this does not hold for propagating light, okay? Because from Maxwell's equations, it directly follows that light propagating in the universe, even if there is a changing speed of light, it just can't adjust its wavelength. The wavelengths would remain constant. So, as a consequence, that's what Dicke proposed. As a consequence, we would have a different explanation, different interpretation of the cosmic redshift, which is not expansion anymore. So Dicke would say matter is basically at rest, and just the light wave remains constant when it's propagating. So with respect to earlier times, we observe longer redshifted light. This is a slide that, it's just nothing else but visualizing. We have atomic scales, we have a contraction of length scales, we have propagating light that doesn't, so light just appears redshifted and there is no expansion of matter in the universe. You see, just matter becomes smaller because the atoms would need to become smaller. So you will arrive at this cosmology with variable quantities, and that's what Dicke developed, but unfortunately he made an error. He didn't consider at one time that you have a perceived time. Just was thinking about that absolute time, but if you look at a perceived time, you have to consider that your clocks are running differently. Okay, so with respect to that absolute time, you have a perceived time which runs differently, and if you look at this, the matter, the total number of particles in the universe is proportional to the volume, but this is seemingly proportional to the perceived time squared. And that's Dirac's second hypothesis. Dirac's second hypothesis is in perfect agreement with Einstein-Dicke cosmology. So there is still this strong hint that Dirac was suspecting, and that's just a common objection. I will just skip that. If anybody is interested, you may ask a question about the Dirac's prediction. Also, this could be explained in that framework, and you even shouldn't wonder anymore about dark energy, because there is no reason, as in Newtonian physics, that the expansion of the universe should decrease. So there is no seeming need for this seeming acceleration. And there is another very interesting test of the expansion of the universe. Not going into details, you can look up that Martin Lopez Correa. And to summarize, based on Einstein 1911 and Dicke's papers, it's equivalent to conventional general relativity. it explains the Hubble redshift from first principles. I think this is an important feature. There is no expansion of matter, just the light spreads and the horizon increases. So there's no need for dark energy. There's a conceptual simplicity, and I think maybe the most important thing is it explains Dirac's observations. And just this, I mean, everybody is talking about the biggest problem of physics is unifying quantum physics with relativity, right? But there is no quantitative idea. It also remains blah blah until you come up with this number 10 to the 39. And Dirac's, that's why it's considered fascinating, Dirac's first hypothesis is still the only quantitative idea to this very basic problem. And it should not be discarded due to this second hypothesis, which also makes a lot of sense. Thank you. You can a little bit more in detail in this paper in Annalen der Physik, and this is a book, Bankrupting Physics. There is a chapter about Dirac, and this is my last book about that idea of Einstein. You need not to be convinced, but I would say just look at the history. There is, and this is undeniable, there is a relation between Einstein, Dirac, and we should therefore reconsider that kind of cosmology. Thank you very much.
Questions, comments?
To your relation of what is 39 orders of magnitude. It is related in the most cases, it has two weaknesses in my understanding. It's related to the size or mass of the proton. For Dirac, it's understandable because in his time the proton was an elementary particle. Now we have a different view. We say the quarks are for both, for the mass and for the size, the elementary particle. So this number should perhaps has to be adapted to this. And the other thing is you have variables there like the radius of the universe. The radius of the universe, you have said it yourself, is expanding, it's increasing. So this can only be relation for a short time, for the present time. Some time later it will be different. That is, and I have another comment, but first this for itself.
Mm-hmm. Yeah, I think your second comment is just a misunderstanding. I mean, it's the very feature, the very exciting feature that it holds over time. But you just have to study these dependencies. The more, if you want, more grave objection is that, we have become so much smarter. We know that there are protons, not elementary. We have quarks and this and that, and neutrinos, and 3 or 4 families of neutrinos. But I mean, it's pretty clear. If you want to take that approach, you have to look at the history and methodology of science. And science has very long time scales, okay? And it takes certain decisions. At one point of history, all physicists go along here. And another possibility is discarded at the moment and nobody will reconsider it, okay? But of course, I mean, if you look at this, you have to go back and then closely reconsider. You're not getting out all the transformation matrices of 4 neutrino families, of course. Yeah? But I mean, the suspicion is that, I think there are other arguments too, that are we really so convinced of our current models? And it could really be that we are in a very, very long dead end as cosmology and also particle physics is considered.
Okay. I have a short question maybe. Yeah. Short.
Another question. I'm not sure it's so short. What is your objection against the redshift, for the Hubble redshift? If you assume the universe like it was classically understood by Lorentz and by others, not by Einstein, that space is expanding, but the stars and material is moving via the receding, yeah? Then, and these stars have to have a redshift by this reason. Now the problem, what people see is the dark energy, because they say this expansion is accelerated But if you assume what you have done, that the speed of light is changing, so the speed of light is slowly going down, and you look how the speed of the stars is calculated. It's calculated using the Doppler effect, applying the Doppler effect to the redshift, and you take into consideration that the speed of light was higher at earlier times and lower now, then the result is that there is no acceleration. And the whole problem, which is said to be one of the biggest problems in physics of dark energy, completely disappears because there is no acceleration. That is a misinterpretation of the speed. The other argument against this, if you follow Einstein and say it's not a problem of Doppler effect and of a material flowing away, but the space is expanding, then you do not have this argument. Then you stick with this problem that you have to conclude, that is what I'm told, and you have to conclude that there is an accelerated expansion. But only with Einstein. If you go to a variable speed of light, then this problem completely disappears. It's just another view on this problem, because you mentioned.
I'll try to answer that. I think the problem of physics is that we don't ask questions anymore. Okay? So, people were observing the redshift, and the interpretation was, okay, it's expansion. We didn't ask why that expansion. It was just, well, it is as it is. So later, when this expansion was scrutinized more precisely, there was something wrong with it. It shouldn't expand that much. It should break in that. No. Yeah. And then why you came up with dark energy. And then there are the other problems. Oh, it's not exactly like dark energy, and then maybe you need another fix. So you're piling up complicated assumptions one after another, instead of going back to the basics and then, why is there a Hubble expansion at all? What's the reason for it? Okay. And a much more elementary first principles explanation would be, okay, there is no need for matter to expand. Just matter stands basically still, and we have only light expanding, and that's how the redshift could be explained. Okay. I know that this is very, very far from any common belief in cosmology, but I think you don't need to believe everything, but I think it's worth going back and studying these papers, which have undeniably close relation to each other.
Okay, thank you. Thank you for the talk, and let's thank all the speakers of the session again.